this will be the review of Chapter 8 and 9, some AP exam multiple choice questions for our test. So let's get to it. Number 10 says, which molecule below has a central atom with less than an octet of electrons? Remember we said that some molecules do not obey the octet rule, and let's find the one that does not obey here. There's a few ways of doing this, but let's go ahead and count the total number of valence electrons available for the molecule, and we'll see if automatically we can see one that has less than 8. In fact, for water, if you take a look at water, oxygen has 6, each hydrogen has 1, we got 2 there, that's a total of 8. If we do a similar analysis of NH3, ammonia, nitrogen gets 5, each hydrogen gets 1, so we also have 8 here. But if we analyze BH3, boron trihydride, we'll see that boron brings 3, each hydrogen brings 1, there are 3 of them, and we get a total of 6. So there is, it's impossible to arrange 8 electrons around the boron if the total number is just 6. If you similarly analyze CH4, you'll see it has 8, and silicon tetrahydride also has 8. So your answer would be C in this case. All right, number 11 says Lewis electron diagrams for CO2 and SO2 are given above, and the molecular geometry and polarity of the two substances are the same or different. Now, we should expect these to be different because of this lone pair of electrons on sulfur. Remember, this will make sulfur bend down, or the arrangement around sulfur bend down. You'll get yourself a bent arrangement, whereas this will still be linear. So we are looking at two different geometries, and let's pick the answer that justifies it. So these are out because they say the same. C says different because the lone pair of electrons on the S make it the negative end of a dipole. This is correct. D says different because S has a greater number of electron domains. It's true that sulfur has 3 electron domains, 1, 2, 3, whereas carbon has 2. However, you can have more electron domains and still be nonpolar, is the idea. So the best answer is actually C in this case. This lone pair of electrons makes this side the negative side, which makes the bottom the positive, and that's how you get your dipole. You get 2 poles. You get the negative pole, you get the positive pole to the molecule. Okay? 12 says, which of the following molecules is nonpolar but has polar covalent bonds? Remember, nonpolar means the whole molecule essentially is evenly distributed in terms of its electrons. Now, N2 is nonpolar. In fact, N2 has a structure that shows a triple bond between the nitrogens. But each one of these bonds is also nonpolar. Between the 2 nitrogens, you have the same pole, the same electronegativity, so it is nonpolar. If you analyze H2O2, this is peroxide, hydrogen peroxide, you'll see that it looks like this, and it is, in fact, the whole molecule is polar. On top, you will have more electron density than you have on the bottom of the molecule. So this one is polar. Water is famously polar, so that one is out. But this one, CCl4, is actually nonpolar because we have 4 chlorines around a carbon, but each one of these bonds is actually polar, and chlorine pulls the electrons toward it. So each one of these is polar. We can represent that with a plus toward the carbon and a minus toward the chlorine. But because they are all equivalent, they cancel each other out, making the molecule nonpolar. So this then would be the answer. This guy here is actually, the molecule is polar since you have chlorines on one side of the molecule and then hydrogens on the other. So this one would be polar. Let's go on to number 13. And number 13 asks us, of the following molecules, which has the largest dipole moment? Now this term dipole moment actually refers to the strongest pole, or the strongest pole difference. So which molecule is the most polar, in other words? So CO is definitely polar because there's a difference between carbon and oxygen. CO2, as we've seen above, is actually nonpolar. So this one cannot be it. Oxygen is nonpolar because it's got 2 of the same elements. Now, fluorine would be nonpolar for the same reason, but HF is polar because you have a difference between these 2 elements. Remember, polarity shows up because there's a difference in electronegativities between the 2. And the question is the difference bigger between C and O, or is the difference bigger between H and F? Well, we know fluorine is the most electronegative element on the periodic table, so it will show the highest difference between it and any other element. So the electron density would be mostly on fluorine's side. Apologies. On fluorine's side, making that the answer. Little sneeze action there. Oh. Okay. 14 says, which of the following compounds is ionic and contains both sigma and pi covalent bonds? Remember, ionic means you have to have a metal and a nonmetal. The nonmetal could be polyatomic. So if you recognize these to be polyatomic, this is hydroxide, this is hypochlorite, this is cyanide. So if you draw these out, you'll find that this one is not ionic, this one is not ionic. This one is actually not ionic, it's an acid. So we have two ionic possibilities, iron hydroxide and sodium cyanide. So the question is, which one of these has pi and sigma covalent bonds? Now, covalent bonds will be in the polyatomic ion. So OH minus, for example, will have covalent bonding, and so will Cn. If we draw both of these out, you'll see that OH minus looks like this. There's a single bond, but the Cn minus looks like this. And there's a triple bond, which means you have both pi and sigma bonds. Remember, pi and sigma bonds exist in double and triple bonds. The first bond is a sigma bond, and the second and the third here would be a pi bond. Remember, pi bonds are the ones that go above and below the molecule, resulting from unhybridized p orbitals. And so this one is then the answer. Good. Let's take a look at number 15. According to the Vesper model, the progressive decrease in bond angles in the series of molecules CH4, NH3, H2O. So what they're saying is that the bond angle decreases as you go from CH4. Now CH4 simply shows 4 hydrogens around the carbon. NH3 shows 3 hydrogens around the carbon and a lone pair. And water shows 2 hydrogens and 2 lone pairs. And customarily, we draw water in a bent fashion. So this is how usually water is drawn, just to reiterate the fact that it's bent. And remember, we said that the bond angle between these two is going to be about 109.5, but due to the lone pair, a nitrogen, because lone pairs take up more space than bond pairs, this will push these bonds down a little bit, closing in this angle. This especially happens in water. These lone pairs exert a lot of repulsive force, pushing these even closer down, making this even smaller. So the best explanation then is the increasing number of unshared pairs of electrons. And that's the idea. So D here would be the correct answer. Okay, let's keep going. See if we can hit a few more here. Number 16 says, to make gold stronger and harder, it is often alloyed with other metals, such as copper and silver. Consider 2 alloys, one of gold and copper, and one of gold and silver, each with the same fraction of gold. If the gold-copper alloy is harder than the gold-silver alloy, which of the following is the best explanation based on the information in the table on the right? So here's the information. You'll notice that gold and copper have roughly equal melting points, but their sizes are different. So I want you to notice the biggest difference here is the size, the metallic radius. So gold and copper is quite a bit smaller, and silver is about the same size as gold. This will probably play the biggest role. And our possibilities are A, copper has 2 common oxidation states, but silver has only 1. Now the oxidation states are the possible charges that these can form. Oxidation states come into play whenever you're undergoing chemical reactions forming compounds. Since an alloy is actually made just from, you can say, physical mixing of these 2 metals, you won't form any compounds, there won't be any loss of electrons, there will not be any oxidation states to consider. That one's out. B says copper has a higher melting point than gold, but silver has a lower melting point than gold. Now, this is true, but melting point actually does not have an effect on the hardness necessarily. Melting point is just another property we can measure. So that's probably out. C says copper atoms are smaller than silver atoms, thus they interfere more with the displacement of atoms in the alloy. This is probably the best answer. Let's circle it, because this is true. Copper is smaller. So if you have a bunch of a bunch of gold atoms, and you have some copper between them, they can help stabilize the gold, essentially. And D says copper atoms are less polarizable than gold or silver atoms. We don't know whether they're less polarizable or not. In fact, polarizability, as we'll see, we haven't discussed this concept, but we will see this, applies to molecules, not to ions or metals. So C actually is the best answer here. Okay, we've got one more. The BF3 molecule is nonpolar, whereas the NF3 molecule is polar. Which of the following statements accounts for the difference in polarity of the two molecules? Now, if you take a look at the BF3, B, boron, is oftentimes involved in having less than an octet of electrons. And in fact, this will be the case here. Boron will form with fluorine to give you a trigonal planar geometry. Now, this will be the structure if you draw it out, the Lewis structure. However, the boron will not have, fluorine will not form a double bond to share with boron. Part of the reason is because fluorine is very electronegative, so it is reluctant to share its electrons. But the other reason is because boron, being in the third group of the periodic table, it can usually withstand having less than an octet. So this would be the shape of, or I'm sorry, the structure of BF3, whereas NF3, in the case of NF3, you will have a lone pair of electrons. That being the case because if you total up the number of electrons, nitrogen actually brings 2 more to the table, allowing each fluorine to have a full octet without sharing. And this, by drawing them this way, you can see then that boron has a trigonal planar geometry, whereas nitrogen has a trigonal parallel geometry. So the best answer for that should be, let's see, NF bonds are polar. Actually, all of these bonds are polar. So D should be the right answer. Unlike BF3, NF3 has a non-planar geometry. So BF3 is planar, but NF3 is non-planar due to the unshared pair of electrons on the nitrogen atom. So that should be the right answer. So go ahead and look over these, think through these yourself, make sure these make sense, and then we'll do the next two on the next video here.